Hello and welcome to your video on finding the reactions for an indeterminate beam using statics and kinematics. Now, kinematics is the geometry, really the geometry of a motion, but in our case, our motion is coming from a beam deforming or deflecting, and so we can say it's the geometry of the deformation, because that's what our motion is. And so we have this beam that we can see on the left side there that is a fixed support at A, but instead of behaving like a normal cantilever, there's actually a roller support also added at B. And we have a linearly distributed load that starts at 0 at A and increases linearly to a constant magnitude of W at B. And I've already drawn the free body diagram. So we're going to have AY, AX we were observing as 0, and a moment at A, which I went ahead and drew in the positive sign convention for a moment at the left side of a beam. And we have our support reaction BY. And we know that we're going to have a resultant of that distributed load that's going to be WL over 2 because of the triangular. And it is located at 2L over 3 from A. So if we want to get started, we can jump in and do the statics, and we will write out that some forces in the x equal to 0 because we don't want to forget that we use that equation to cross out AX. But then we could take moments at A. I'll go ahead and do this one clockwise. And so we'd have negative BYL plus WL over 2 times that 2L over 3. And then we have to add in M sub A because it is a constant. So we could write out that MA is just negative WL squared over 3 plus by times L. We can do another statics equation. I'll go ahead in some moments again. I'll go counterclockwise as positive. We could have also summed forces in the y. But we'll get another equation again with MA because that's still a constant. And this time we can write out MA is WL squared over 6 minus AYL. And so we have now two equations left, but we have 3 unknowns, and that's problematic. So what can we do to try to find these additional equations? Well, it turns out that we can actually use what we know about the deformed shape. We can use the kinematics to actually give ourselves an additional third equation. But the only way this is going to work is if we get our equation of the elastic curve or our V of X equation. Now, to get our V of X equation, and not even just to get our V of X equation, but if we're going to say that we know something about the deformed shape and that's going to help us get a third equation, let's make sure we sketch and visualize what the deformed shape is going to look like. So if we go back to our main beam, we can draw our deformed shape, and that's going to start out with 0 deflection at A, but also 0 slope, coming off like a diving board. Because of that moment at A, it pushes away any rotation, and we get 0 rotation, 0 slope at A. But now instead of just going off like a cantilever and having our maximum deflection at B, because of that roller, we're going to come back up and have 0 displacement also at B. All right, so if we want to write our V of X equation, we actually first have to write our M of X equation for this and integrate it twice. So we need to make a cut. Fortunately, we can make our cut anywhere along the length because our cut will be valid from 0 less than or equal to X, less than or equal to L, because our load is constant, it's not discontinuous. And so went ahead and drawn the cut and labeled everything that should be on it. We'll still have our AY and our M sub A. I've drawn the shear at the cut and the moment at the cut in the positive sign convention. And then I've also labeled the magnitude at the top of the cut as W times X over L. So it has to be a ratio. Now, if you're curious how we got that, we can have a little aside here. And I actually was able to solve that just using similar triangles to write the equation for the load as a function of x. So we have our w of x equal to wx over L. So if we just draw the load that we have over the whole length of the beam, the full triangle, and then we can also draw the load that's on our cut. Now we have the full triangle, length L, cut, length x, and we know the magnitude for our full load is that constant W, and for our smaller triangle at our cut, we're just going to call that some function of x, right? Because it would vary in x, and we know we vary linearly. Well, these are similar triangles, meaning they have the same height. I'm sorry, let's try that again. They have the same angles. They don't have the same height, but they have the same angles. So if you took cosine, sine, or tangent, you basically just be comparing, well, especially if you took tangent, the height to the width. So we can just compare the height to the width. So we'd have W is to L as W sub x is to x, or W sub x is just that Wx over L that we've shown already on our cut. You can check the validity of your equation by putting in your outer limits of the equation. So at x equal to 0, you should have 0 load, which we would have at A, and at x equal to L, you should have a magnitude of W, which our equation gives us. So if you're comfortable with that, we're going to go back now and keep solving our equation. So let's just jump in to where we were at, and now we're ready to do our statics. We'll want to find our resultant, which would be at 2/3 of x from the left side, and we'd have Wxl times the distance x times 1/2 as our resultant. So if we sum moments at the cut, so we don't have to find the shear at the cut, we just sum moments there and it goes away. We can go counterclockwise positive, and we'd have our negative ma minus ay times x plus wx squared over 2l, our resultant, times x over 3 plus that constant m of x. And then we just rewrite this whole equation for m of x because that was our goal, so that we could integrate our m of x. When we first integrate the m of x, we're getting our slope. That's just 1 over ei times the integral of the moment expression. And once we actually take that integral, we're going to get back out that we have the slope equal to 1 over ei times the moment at A times x plus a sub y x squared over 2 minus wx to the 4th over 24L and plus a constant of integration C1. Now we've already looked at our deformed shape, and we actually observed something about the slope. So let's go ahead and jump right into a boundary condition. And in this case, the boundary condition for the slope, which we said at A, the slope is 0. So if we were to plug in theta of 0 is equal to 0, we just get back out 0 plus 0 minus 0 plus C1 equals 0, so C1 equals to 0. And that can now simplify our equation of the elastic curve when we integrate the slope. We no longer have to bring in the C1 expression, so we'd have our integral of our m sub ax plus ayx squared over 2 minus wx to the 4th over 24L, and we can just take the integral of that, neglecting C1 since it's 0, and we get back out 1 over ei times the quantity of ma x squared over 2 plus ay x cubed over 6 minus wx to the 5th over 120L plus C2. So once again, we want to look at our boundary conditions. But interestingly enough, when we apply our boundary conditions for displacement, there's actually 2 different boundary conditions that we know. We know at x equal to 0, the displacement is equal to 0, so we could plug that in and we'd have 0 plus 0 minus 0 equals C2. I wrote plus, but it doesn't matter because C2 is still 0. But we also have at x equal to L, at B there, we know the displacement is 0. So when we plug in x equal to L, we suddenly get a useful equation, and we'll have ma L squared over 2 plus ay L cubed, that will be corrected, minus WL to the fourth over 120. So let's correct that cube squared and make that cubed. All right, so we now have a third equation. So we're able to then combine our two statics equations with this third equation that came from kinematics. So specifically, let's go ahead and put equation 2 into equation 3. And so we'd have our WL squared over 6 minus AYL now multiplied by our L squared over 2 plus our AY cubed over 6 minus WL to the fourth over 120, or we even set it equal to that. And now AY is our only unknown, so we get back out AY is 9 WL over 40. Plug that back in to equation 2, and we'll get back out now our M sub A value, and our M sub A would be negative 7 WL squared over 120. We could also rewrite that as 7 WL squared over 120 going in a counterclockwise direction. Finally, if we just rewrite now equation 1, knowing what our values are for M sub A, we can solve our BY, and we'll have BY equal to 11 WL over 40. And so we have our final answers. It's not a bad idea to show the direction of all of the resultants so people don't have to go back and look at your free body diagram. And as a final check, that some forces in the Y that we talked about at the beginning, if you're going to do moments twice, it's good to do moments twice when you do your statics, because then your sum forces in the Y should equal 0, and it's a nice little quick check. Well, when we sum forces in the Y, we get basically 1/2 WL, which is the load. So congratulations on finding the support reactions for a statically indeterminate beam using statics and kinematics.